All right, hello everyone. Here for a bit of late night coding with me, Halgari. No camera today. As it turns out, it was so nice yesterday. I went on a bike ride. Completely fell off my bike. Tire exploded actually, so no one wants to see the way I look right now, but I am feeling okay. So we're just gonna keep the camera off in case any sort of weirdness. Wow, I just don't want to run afoul of YouTube's guidelines as far as blood and gore, so we'll keep it at that. Yeah, today we're gonna look a little bit at this paper called muKanren. It's one of my more favorite programming papers. It shows how to write a logic programming language inside another language. This is really kind of cool stuff, and it's kind of, if you're really familiar with Prolog, if I could talk tonight, or something of that nature, that's what this is going to look a bit like. Well, not look like it, but it will be a bit of a way of embedding a logic language that works a bit like Prolog. I'm kind of loading this into my mind because I want to think about it some in the next couple of days as we do some work on the Nexus Mods app to see if maybe we want some sort of query language like this. And it's been a long time since I've looked at something like this, so I want to kind of be looking at it today. So one of the first things we need is what's called an LVAR, which is just a class with a name, optional name tied to it, an ID. And so we're gonna define that right now. We have an int ID, a name. And what we're doing is a basic implementation of this. I'm not going to try to make it look nice or make it fit well into the C# programming language. We're pretty much just going to implement it up straight as is. So ID equals, well, we'll assign that. We'll do a static thing here. So every time we make a new one, we'll get a new ID for it, right? So what we're going to do here is private static int, and then this next ID is 0, and then every time we create one of these, we're going to set it to the what's that called? Interlocked increment ref next ID. So this will do an atomic increment of the ID each time, and then we'll make a getter for this. So this does an atomic update. Even if we have multiple threads creating these at the same time, each creation of this LVAR will make a new one. And I guess in that case, we don't actually need the ID up here, do we? We just need the optional name. And then we'll do a public toString, public override string, toString. And I want to actually expand this and say if string dot is null or empty name, then we'll do this. Otherwise, we'll return not the name so much. We'll do LVAR name. Yeah, that works. And then we'll actually give this in case the names are allowed to collide. So we'll do underscore ID and then underscore name right there. We want the actual name, don't we? So this will allow us to get the name if we have it. Otherwise, we'll get the ID at the beginning of it. And this is wants to rewrite. Nah, we're not going to rewrite that. And then we'll override the equality. But we don't. We want to make sure this is only if they are the same. So reference equals. So this will say that they have to equal exactly. The two have to be the same object for them to evaluate the same thing. No, we don't want that. Okay, so they're like singletons here, right? So if the other one is the same instance as we are, then we're good. And then we're going to override the hash code. You're supposed to do the hash code and the equals together in C#, and so we'll go ahead and do that. Get hash code. So we'll do the hash code of ID. Now, what's it complaining about here with ID? Non-read-only field. Well, this should. Yes, that can be read-only. No, that's fine. Okay. So now we have this LVAR, right? Now we're going to write something called unify. Unify. So the way this paper talks about it is when we're creating this logic engine, it's a way of defining relationships between values and these LVARs. And the way we do that is through this infinite stream. Now, this paper uses monads. We're going to start tonight with enumerables, and then I might look a little later into what it would take to do it with monads in C#. That may not be worth it, but there's some things in C# that are different than in other languages I've used. So we'll look at that later. So first of all, let's look at here what we have as far as unify. I have to look this up every few times. So public static, and this will return a. Wow, I don't know what that's spitting out. So this will return a environment. So we need to define what our environment is as well. So an environment. An environment is a thing that holds relationships between one thing and another. And for now, what this is going to be is really nothing more. You know what? For tonight, for the simplicity of it tonight, we're just going to do this up like you would do it in a Lisp. So we're going to find this as a public. We'll do a private list of LVAR to an object. So we're just going to scan through this thing until we find something that it matches to. So we're going to do public void, public, what are the two here? It's walk. So we see that here, walk, and this is in Lisp, but, or Scheme specifically, but well, that'll be fine for today. And so what we're going to do is we're going to do a walk first. Let's see here. It's been a while since I've read some of this. So we're going to walk. So let's do walk first. Public object walk, and we're going to get a lvar var and then an environment. So we're going to look up the lvar in the environment, and what we do is we keep walking this over and over again until it terminates at an object or at nothing. And the way we do that is say, well, this actually looks fairly fine. Find. That's actually exactly right. So what this says is, let's reorganize this. Now, obviously, this is not going to be the fastest thing on earth, and that's not really what I'm trying to do today. I've kind of written systems with this so much that I kind of want to take time to walk through this, no pun intended, and kind of page it back into memory here. So what we're saying here is we are going to find the first match where the first item, and we can name these pairs here, lvar and value. So we're going to go where the first lvar equals the var we're looking for, and then we're going to say if the value we pull out of here is itself an lvar, then we're going to recurse back up and do this again. And what this allows us to do is we can have like chains of lvars. One lvar can point to another, to point to another, to point to another, right? And then what we just have is bind as well, right? Or extend, I guess is what it is. And then we're just going to add a lvar and a value into this and return a new binding. Now this is not what we want, because we actually want to return a new binding. So we're going to go up here and do a list of lvar and then object and value bindings. And then we're going to delete this because we don't need it anymore and change this to just normal bindings. And then what we can do is we can extend this other one, right? Now this is kind of like a poor man's immutable dictionary. I guess we could use that here too. Is that what we would want to use here? I mean, that would work. Fair enough. Immutable dictionary of lvar to object. I was just trying to make it simpler before, but I guess there's really no point. So those are our bindings. And then here we can just say if bindings dot try get value, so we're going to get it out and then say if value is lvar, then we're going to walk again, otherwise we're going to return the value that we found. Technically we're going to do that here, because if we get nothing at all, then we're just going to return the var itself, right? So this didn't actually bind out to anything. Convert recursion to iteration? Yeah, I suppose, but that's a weird thing. We're going to do that later. All right, so then what we're going to do is say return new environment where the bindings, we've added the bindings in. And this is going to return an environment. So it's an immutable environment system, right? And there's ways of improving this and making this cleaner or whatever as we go along. All right, so next thing we're going to do is, so we have extend, we have walk and extend. And now we're going to do the basics of Unify. Now for now, we're just going to do the very basic version of Unify that we see right over here, which says we are going to take, and this is going to return a environment, possibly, and it's going to say UVS, right? So we have object U, object V, and then environment S. Like I said, we're just kind of do a straight up translation of this. I'm not gonna do a whole lot of renaming or anything. So we need to now go through this whole thing here and say var U is going to be walk. We're going to walk that and walk V. Now it's complaining here because we're redefining these. I don't know if we'll ever need to keep these. They don't. So we're gonna just do it this way. Now it says here, we do need to make an overload of walk. Object walk with a value. And what says if it's not an LVAR, then we're just gonna return this, right? So we can only walk in the environment with LVARs. And now here we go. We got our two resolved. So now, this is funny because somehow C# is kind of knowing what we're about to do, or not C#, the GitHub Copilot kind of knows what we're building here. I don't know if it's read too many of these papers or something, but we're gonna just go through this and say, okay, we're gonna take, if the first one is a LVAR and the second one is an LVAR, then if the two are the same, then we just return the environment as is. Otherwise, we extend, is that correct? Let's see what this says here. So if it equals and equals, then yes. Then we return the environment as is. Otherwise, so they're breaking this out, and I think we will too. Well, no, if they're both LVARs, it really doesn't matter. So it would just fall through the clause, right? So we can say here, and UV, then we just return S. And what this is saying is that if we go into the environment and we so if we go into the environment and find out that both of these are LVARs and that they're the same LVAR, well then we're done because this is all resolved. Now what we can do is we can say if U is an LVAR, then we're going to extend this. Oh, great, we're running afoul of some fun. Binding, we're running afoul of some fun binding stuff here. Well, we'll do it this way. And then if V is LVAR, VL2, then we extend. So see what we're saying here is that if U is a logic variable, and we get to this point, then we know V is not a logic variable. Or it could be, but it's not the same logic variable, so we unify it. Right? And the same thing here, with the opposite way around. And then the final one that we actually don't have here is else. We say if U equals V, then we return S, otherwise we return null. Can we turn this into a switch statement? What does that look like? Nope, that looks like a horrible switch statement, doesn't it? So we're gonna keep it like this. All right, so this is all a little weird. Let's see what we can do. Otherwise we return null. And what is this complaining about? Member names cannot be the same as their enclosing type. Oh, okay. What if we move this into the environment? We could do that, right? We could just have environment.unify. And then instead of S, we just do this. So we say walk and walk. And this isn't static in that case necessarily. We'd probably always want an environment for this. Return this. return this dot extend, this dot extend, this. There we go. Okay. So now, we can write a test for this add class. And we're going to call this basic unify tests. And we're going to do fact. Unify LVARs. Let's see what this has. Let's do a thing here that allows us to make an empty environment. Public static empty equals new environment. There we go. Yeah, we can make this a struct as well. I don't think there's a problem with that. That would reduce a little bit of memory usage, right? Constructor must have a body. Okay. Well, doesn't it though? Does this work fine with a class? No? What am I missing here? Public static empty. Does that work? What's going on here? Cannot resolve stamp public. Oh, A and V. That's what my problem is. Okay. There we go. Empty environment. And then what we do is we can just change this environment to empty. Equals environment.empty or env.empty. And if you ever looked at like programming languages that have like an environment of locals and something of that nature, locals and globals, that's really the way this thing kind of works. Yeah. All right, so now let's take a look at, let's build this first of all, and then we'll take a look at the tests and see what we got. Okay, so what we're saying here is we have two LVARs, and then we should be able to walk them both and see that they are the same, because this one has been marked, LVAR1 has been marked to equal LVAR2. The result should not return null, and then that should work. No, we should do this. Result that should not be null, and we need to pull in. I want to pull in fluent assertions. Here we go. Cool. And then we can just do it this way. A result should not be null, and the other one. Looks like I got a message here. Hold on. Oh, something else. Okay. Never mind. All right. So walk of LVAR1 should be the walk of LVAR2. Do we have a B exactly? Dot B. Let's do B because that should also work. So if we build this then, and then we go to our where's our unit tests? Unit test coverage. Do I already have unit tests pulled up? I've kind of redone how some of these look at times, and also I moved it over here the other day, didn't I? Cool. Cool. Can I move this to the bottom? Just so that we dock to move to bottom left. There we go. All right, so that works. So this may be a little bit hard to read, but essentially what we're saying is that we're going to take these LVARs and put them both into the environment that ends up adding them in. So let's do some other facts, right? Unify LVAR with a value. So here we're going to unify LVAR with 42. And what we're saying is, hold on, we'll talk about this in a second. We're saying that the output environment should not be null, and that walking the LVAR should be able to, yeah, hold on. My wife has asked me a question. Cool. All right, so now what we're going to do is, so we say we put the LVAR in there, and we say the value should equal the LVAR. Oh, so we're saying we're bound the LVAR to 42 in the environment. And then we're saying that the result should not be null because we've had a new environment, and walking the result should give us the output value that we expect. Right. Cool. Now, this is a little weird. So let's do it like this instead. Let's do instead of fact, let's do inline data, and then let's do theory. And can we do objects here? B. And what we're going to say is 42 and 42 should work, because two variables. Well, we can't put the variables in the environment, can we? Nah, we're going to keep this split out for now because that's going to be easier to actually figure out for new users here what's going on. So we'll do that with a fact here. Cool. Okay, now what's interesting about this is that we can also run it backwards. Fact public void unify value with LVAR. So here we're going to do it backwards and say we're going to do the value on the left and the LVAR on the right. Does this actually work? It should. Yeah, it does. Let's see why it does. Oh, that's because we get to this part and we say, is U an LVAR? Well, no, it's not. Well, is V an LVAR? Yeah. Well, then we go the opposite way. Although I think we've actually, yeah, we've, so in this case, it's kind of the opposite of what we just did. Up here, we're saying LVAR is 42, and down here, we're saying that 42 is LVAR. So it's kind of backwards, flipped around. Why does that matter? Well, we'll see in a second. So we can also unify void, unify values. We can say that 42 is 42. And tell you what, let's make this a bit simpler. 42, 42, right? Now here we're not adding any new information to that environment, so we don't actually need to check the environment itself. That works. But for, we can also say result 42 and 43. And in this case, the environment's going to be null. And it's going to be null because 42 is not equal 43. So the way this signifies that these two are not equal is by returning a null environment. Now you may be wondering why we care about any of this. It makes a little more sense in a second, don't worry. So this should not be null because 42 is 42. All right, now let's get to actually something that is a little more fun, right? Instead of unify, let's do goals here. So we don't have anything unify anymore. So we're gonna do add class goals. So in this initial design, a goal is going to be something that is an IEnumerable of environments that takes a IEnumerable of environments and does something with it. So we're going to make this a static class. And what do we do here? I guess we make a range. We can make a range first, right? Range. IEnumerable of environments. And what we're going to do is int start, int end, and then LVAR out. So what this is going to say, I don't think this is what we want at all. This doesn't have the foggiest clue what we're doing. We're gonna do a basic version of this. For each environments, what we're gonna do is we're gonna say for each I in between those, we're going to extend it with the output equal to 1. So this is like complexity of O m of n, right? For each environment, we are going to get the number of things out that equal to this, the distance between start and end. And we have a problem here, non-static math, okay. And we'll do this just to make this look a little bit nicer. Okay, now we also need this equality operator, public static equal. Let's call it equal for now. We normally want to do something different here, but we have an A and a B. And all we do is that in every environment, we unify A and B, and if the result is not equal null, we return the result, otherwise we cut it out. So add class, goal tests. And what this will do, so we'll do our first one here, fact. Get, let's do, can run range. We'll just do that, right? We need one more thing here too, which is a couple more here. So we need a public static enumerable of env query. We're gonna just call this query. This is not in the paper, but it's a kind of our way of setting this up and returning things. And all we're really going to return is a environment.empty. So this is going to be the start of our query. And then what we're going to do is have a run. Public static enumerable of t. And we're going to run t. And this is just going to return actually no, not a t, this will just be an object for now because we don't have anything typed. We can type this, but lvar output, yeah. So what this is going to do is like for every single environment, we're just going to walk the output and return this. We won't use this at first, but it'll give us a example of what we're looking at here. We'll do some debugging of this. Var result equal query. What was that called? That was goal.query, right? Goal.query. And then we're going to do .range 1 to 10 or to 20. And we need an lvar to put this in. So we're going to make a new lvar and call it output, right? Let's actually name it output. Okay, this is when it starts to get fun. So if we look at this here, we're just going to go here, result dot to array. Oh, can we? There we go. So we're just going to go here, and then we're going to compile this again, and then run that specific test here. And what we're going to see is that our result is an enumerable of something. And actually, you know, we should go into, so let's look at what our result is right now first. So we have 10 results as we expect. The first result has an environment that is empty. Interesting. Oh, it's an environment, but we don't have a way to list any of these things out, right? So I'll tell you what, let's do this. Let's go to our environment and make this a little bit easier to look at. Public override toString. And what this toString is going to do is just join the keys and values together so that we can see what's mapped to what within this whole system, right? So then let's do this again. And the result here so we have that's interesting. I thought I had that write that out differently. Why did that? Oh, this is the, okay. I wanted a nice little arrow system there so we could actually see what was going on. So we'll do this again. So what we see is for our results is we have a list of environments, and the first one, this is all mucked up, isn't it? We'll have to fix that in a second. But yeah, shoot. All right, let's do that again. Key value. Why is that? Though the key isn't printing out correctly, our LVAR print code up here is not. Oh yeah, because I didn't put a little thing here. There we go. Okay. Because I wanted to see both the ID and the name, and what we'll see is that these are all the same thing. So let's see, LVAR 1 is 10, LVAR, then it's 11, then it's 12, 13, 14, 15, 16, and so forth, right? Now what's kind of cool about this system is we can start to do even weirder stuff here. So range 10, let's do 5 to 15. And we'll put that in output too. Var output equals new LVAR output 2. Not output, yeah, well, output 2, and then we'll do output 2 here. And then when we run this, what we'll see is we have even more environments. So it's 100 times 1, or sorry, 10 times 10 for a total of 100, right? So we got tons of them here. Because what we'll see is that we have 10 and 5, because that's the first pair, and then 10 and 6, 10 and 7, 10 and 8. So we just created a stream of environments, right? Now, how do we constrain this? Well, we do dot equals. We say we're output is equal to output 2. That's not static for some reason. Nope, because we want, was it equal? Yeah, not equals, it's equal. Cool. So now if we actually run this, what we see is that we should have less results. And we do. In fact, we only have 5. We only have the ones in which output 1 and 2 are equal. Now what's really cool about this is that we didn't necessarily have to write this, like how to figure this out. This can be run in any number of ways. Let me make sure I built this correctly first. So instead of this extend here, we don't actually want extend. Which we want is result equals env.unify, and we want to unify the output with our value. And then if output does not equal null, then we return the result. And there's a key reason for that here. It should be cutting the dead clauses or the dead subparts of this query. So if we run this, we'll get the same result. Well, no, it won't, because we didn't fix the test up yet. But if we look at our results, we get the same results here. So let's fix the test up first, and then we'll see something really kind of cool about this in just a second. So what we can say is we have our range. So the output of this, we want to do that run thing. And we want a variant of this that takes 2. So output 1, output 2. So this one only takes 1 clause. We're going to do one that takes 2. And we'll just call this O and LVAR O2, O1 and O2. And we'll put these in a tuple. So this will now we'll return an object and an object, right? O1, env walk O2. So we're just going to pull these out for easier use. And then if we go back to our goals test, we can just do output and output 2, right? And what's this complaining about? It's complaining that did I work that up before? What's complaining about here? So, because it's taking a T. We never did take out the T, so it doesn't know what the T is because it's not used anymore. Okay, so this returns an enumerable of objects and objects. And if we run this yet again, what we'll see is that we'll just have all the pairs. It'll be the same value every time, right? So what we can do here is we can make some assertions about it, right? Result.count should B5. And we'll do a to array at the end of this so it stops complaining about us reevaluating it over and over again. And then we'll do result like for each var pair in result. Pair 1 should be item 1 should be item 2, right? Because they are equal. And when we run this, what we'll see is that, yeah, in fact, that does work. Now, here's where the real beauty of this sort of thing comes in. If we've built this right, if, it's a big if, this works. We can say output 1 equals output 2 at the beginning. Yeah, sure enough, output 1 and output 2 are the same. And down here, we have that. This is very declarative. We can put it like this. That'll work. We can do it like, what else have we haven't not done yet? When we put that here, we can switch the range clauses, right? Any of these things can be run. We call them running it forwards or backwards, but at any point, the output 1 and output 2 may be in the environment or maybe not. It's not really something that we care about necessarily. The system will kind of figure it out on its own. Now, there is some performance things to that, right? I think putting it up here may run slightly faster. At these values, it probably doesn't matter so much, but 1,000 times 1,000 items or whatever is a problem. Now, the other thing too is, I mean, this range could short circuit, right? So we can look at this and say, hey, if we walk the output and the output terminates to a specific value, then we can skip everything in this range that is not that output, and we don't even have to generate that environment. So by just adding another if clause here, we can improve the performance of this in case someone's wrote something really dumb like this. Now, only 100 matches is not a big deal, but if these were both 500,000 or something, we would notice a performance drop. So having some shorter, auto cutting clauses to that or goals would definitely help. Okay, so the other thing I wanted to implement tonight, and I am realizing after doing this that I am feeling a bit more tired than I thought, but I do want to get this next part done so we can take a look at it a little bit. And that is, we want to make an LCONS. So if you aren't familiar with Lisp, you're about to get a bit of a crash course on it. A cons cell in Lisp is something that has a head and a tail. And in our case, the head and the tail can both be objects, and they can also be LVARs. And here they want to call them car and cooter. A little bit of a Lisp background for anyone. Car means current address, or item at current address or whatever, and cooter is the decrement of the current. I don't know what it is. I thought I did, but it's been too long and I flushed that out of my memory. What's better is a head and tail, right? And that's all that is. In fact, let's just make it a record so that we can tell what's going on here. And then, we'll do a little thing like this, and then we can do public static to cons to LCONS, and we'll do this IEnumerable of just an IEnumerable, right? List. Skip one. Why is it complaining that this is? This would be an IEnumerable. This would be an LCONS. Now, why is it complaining here? This could be cannot resolve two LCONS. Oh, because this isn't in a static class. Public record or public static class extensions. There we go. Well, that will turn it into an IEnumerable. That's kind of cool. And then public static. Is it object? LCONS. to, well, what do they want to do here? Why would they want to return null if it doesn't have anything? Otherwise tail is, I mean, I guess that works for now. Yeah, whatever. Cool. And then this is numerator. No, we're not going to do this, folks. Goodness, I just want something simple. There we go. Yeah, that's all too much for tonight. What we're going to do instead is just public object tail. We'll return the tail. Cool, that'll work for now. Okay, so what we're gonna do though is extend our walk and our other stuff to, maybe not walk. Yeah, I don't think that gets updated, but I think goal of the environment does here. So we gotta kind of implement this point here. Oh, we do need a pair. So let's do public static bool is pair object A. Yeah, so that'll just be lcons. And then what we'll do, so this gets a little interesting. So it says if lcons dot is pair u and don't know that we need to, well, okay. And we want to, then we do this, and if that's not null, we do the tails. Cool. Yeah, this is a little weird. But we're going to look into this a little bit, how this works, and we'll figure out how much further we want to go. So let's see here. Let's do add class lcons tests. So what's interesting about this is that if we can start to build up some more complex logic now with this sort of thing. And what have they built for us? Okay, let's see what this is. We have 1 and 2, 1 and 2, 3 and 4. And then we have an empty environment, and we unify the two conses together. So now 1 and 3 should be equal, and 2 and 4 should be equal. 1 and 3, 2 and 4. Well, yeah, thanks. That's exactly what I was looking for. Not all paths return. Oh, in the other case, we return a unification. Yeah, so if it's S, we return we don't have a default clause here because it came here, so we don't have an else. But I think that's actually just this, right? This is the else. And it falls out. I think that's right. Yeah. Okay. Now let's make ourselves a helper here because we are going to want that. Remind me again how we construct is it at all? Is that what we're looking for? Public. Kind of want it empty. Okay. We just want some helper classes on here. Enumerable object, first of all. So we'll make ourselves a nice getter for all these. So while, so var this, so current is this. And then while current is an lcons, oh, can we do head, tail? No? Casey, what are you doing here? Head, tail? No? Okay. It's just like, well, current is, I don't know what they're doing there. I don't know why that was recommended. That doesn't make sense to me. Use not null pattern instead of type check, succeeding on any non-null value. Okay. Whatever. Okay. And then if cons.tail is not an lcons, then we return that and break. Yeah, I suppose. It's a little weird. Else the current is the lcons tail. So we're just looping through this and taking the tail, and that becomes our new object that we're looping through. And now we need kind of the other way around, which is public lcons, and we're just going to make our, actually let's just do the array syntax. Public static lcons, and what we can do is like rams object. So ACK, it's null. I mean, this is recursive, and I'm not too happy about that, but whatever. Oh, if it's, well, not, yeah. This is a little bit weird converting this over in this way, but okay, we can do another one here. Fact. So what we get for free out of this is something like this structuring. So can destructure lcons. So we're going to make two lvars. And then what we're going to do is make a cons, lvar cons of that. And then what we're going to do is var lvar cons2 is, and the second one is going to be, oh, we actually want create here. Cons.create. Do we not make that public or something? Where's the create function? Public static cons, lcons. LV1. What's this saying? Cannot resolve symbol. Did we put that in the wrong spot or something? Did I name it the wrong thing? Might be late for me or something. I don't know. What's this referencing? Okay, that's referencing that. Oh, cons, create, not create. There we go. Okay, so now, so we create a lvar with the two lvars in it, and then this one is going to be lcons.create 42 and 43, and then what we can do is var results equals query goals dot query, and then we're going to do dot equals lvar cons and lvar cons2. Now, because these unify and these unify down into the individual items, what we should see is that lvar1 equals 42 and lvar 2 equals 43. So then we do run equal dot run, and we do LV1, LV2, and this should be 1. Yeah, we should have only one result. Yeah, and the first result should be 42 and 43. And with that, let's see what sort of trouble we get into. Can unify outcomes, is that what we want? Oh no, we want to build this thing first. And this is complaining that must have a return type. There we go. And then we run this, can destructure. Cannot do a cons with no elements. And who is doing the cons with no elements? Oh, that would be right down here. We're going all the way down to where it's 0. So what we want instead is if items.length equals 1, then we're just going to do this. And so it has no tail. Yeah, that's going to be a problem, isn't it? Because U or V could be null on this point, because we do accept nulls in this language in the paper. There we go. And let's just see what that really gets us here. So when we go down here, we see this result is in fact that we have 42 and 43, although all we put in were these 2 LVAR cons, and then we pulled the LVARs out, right? All right, so what if we do one last one that's kind of weird here? Towards the end, we talk about, I'm not sure if they have it in here, Conzo and Appendo. Well, we can write some other primitives because they are kind of interesting. So now that we have those cons, we can actually do things like walk over them and some other really weird stuff with it. So IEnumerable of environments, and this is going to be first O. So a common thing in muKanren is this concept of putting an O at the end of a thing that, excuse me, that's a relational operator. So what we're saying here is we're going to get, sorry, I have hiccups for some reason. A series of environments. And each one of them, we're going to get out a, for each one of them, we're going to get out a specific cons, of which we are going to get the head. So that would be like this. And then for each, well, actually, there's a couple ways we can do this, right? One of them is we're going to do the pure muKanren way of doing this, which is var temp lvar equals new lvar, and this is going to be rest. And then what we're going to do is, yeah, pretty much that. So we're going to say it's an equals of a lcons create of the head and the temp lvar. So let's give that a try. Fact. Can get first of lcons. So we're gonna do this a little bit differently. We have yeah, we're gonna do this completely differently. Lcons 1 var lcons 2 Well, you know, we're just going to do the 1, and we're going to do a different number. Let's do 12 and 17, right? And then this is what we're going to use to get stuff out. And then we're going to do this. And what we're going to say is first O of lcons 1, and we're going to put that in LV2 and then pull out LV2. Now this is complaining because first O here should technically take an object, which we can do because this is the level we're working at in this function. We can just change this over and this will work. And then this is saying run. This still had that type requirement that we had before, right? So because we have this first O, this should only ever have one element that returns, and the first one should be 12. And let's see if that's correct. So yeah, it is. So what's interesting about this is that the contents of this first O are themselves built out of this muKanren thing. So you see it's kind of like an embeddable language, right? The sister function to this, of course, is public static resto, which does the same thing. We get a head and we stub that out, and then we return the tail. So if we do this sort of thing again, we're going to find something a little bit interesting here, and that is this is in fact not 17. Because this is actually, these con cells are it's not like this is actually an lcons of 17 and nil, because nil marks the end of the list. That's the way that works in Lisp. So if we do this now and get tail of lcons, what we'll see is this was wrong because we didn't do resto. And if we run this, it'll complain that it's not equal. Oh, it should have complained. Why is that not complaining? Actually, I fix these all as well. So what's the complaint here? Let's go here. Has one thing that's 17. That's weird. When we create this, how are we actually creating the situation where we have one item? Tell you what, let's stop this, put a breakpoint in this create for when we do this. First time we should have 2 items, which we do. So we don't have 1 or 2. We have a head, which is 12, and then this is that getting the subarray. Not super efficient, but we don't really care here. So now we have 1, and this is that. So our tail is 17 dot, right? And then this should return. So lcons 1 is raw view. The head is 12, the tail is 17. That's interesting. So is it in the resto? This should end up being the entire tail, not just the... Oh, we're not doing a for each over this either. What's going on here? Oh, we're doing the equal. Yeah, that's fine. We're doing an equal. So let's go here. So let's just you know what might be helpful here is we do a debug. Well, we'll add debugging into this in the future, but for now we'll just step through this and see what happens. Okay, so let's step into this equals. Okay, we create that and that. Okay, so our first two are A and B. Okay. Oh, so this is interesting because we've created it in this way. Yeah, that's wrong. In this resto, and so the problem is that we have actually handed these two, we've handed them to create and not the new the Elcons constructor. So what you were saying, we wanted this to be the second item as opposed to being the entire rest of the collection, which is what they should be technically. So that if we want to get the rest, we can do it in this way. So now this test should fail, correct, because 17 does not equal nil whatever. But what we can do is, so we get the resto, then firsto of LV1, we'll need another temp var here, our temp 1. And then what we do is, so firsto of, we'll call this temp 1. And then this is, firsto of temp 1 is LV1. And then we return LV1. And then we run this. And then this should pass. Yeah, it does. Okay, so one more thing I want to do before I'm done for tonight, because I am starting to feel this, is something called Membero. I don't know that they list that here. Yeah, so what's kind of cool, first of all, about this muKanren is this is the entire definition of this mini logic language right there. Just that much Lisp. And it's really kind of cool. There's a thing called muKanren, which is more full featured than this, and aKanren, I think, which is alphaKanren or something, I'm not sure, but which is extremely well featured, has a lot of nice things of constraint solvers and the like. I highly recommend this paper. I think I put it in the link or the description of this live stream. But give it a read. It's really kind of interesting. One of the things I'll mention is they talk about streams here. That these streams of environments is what they're talking about. So if we look at our goals, we're just taking a stream in, transforming it, and maybe releasing a new item into the new stream. So like for each item we take in, we do something and put it in the output. You can implement this in any number of ways. You could do this in Go with Go channels. I've done that in Clojure with channels like that. You could do this with enumerables. You can do it with iterators. You can even have it spit out an AST that you then compile down to some language. It's also possible. It's really kind of cool. So let's do another one. So another thing that is also sometimes useful to do is to get rid of these environments or hide them somehow behind. That's kind of what the monads are. They're using monads here where you're kind of returning a stream thing, and that thing can then be injected later on, and you can kind of compose these. So maybe we'll do another stream after a while, another day that digs into that. But for now, let's try something called Membero. And what this is going to take is this IEnumerable of environments. And it's going to take an object, which is a list, and an item. And we don't have a disjunction, do we? Ah, fun. So far, we've been using purely conjunctions, which are conjunctions are a kind of an and you see that in our goals over here, that when we are working through this, we goal tests and a disjunction interjects an or, so you can have an or of two clauses. So I think we probably want that, and let's do a disjunction. Maybe down by our equals. Where did our equals go? Equal. Public static IEnumerable INV. We can call it disjunction We'll call it an OR. And this takes a this of IEnumerable env1s, and it's going to say function, and we're going to pass in a so this is going to take one or more functions that take an IEnumerable of env, and they return an IEnumerable of env. Clauses. And this is going to be a little weird to implement. And what is this complaining about? So this is where it gets weird with enumerables. Because, and we're just going to do this in a very simplistic way that will work for tonight, which is our previous equals dot to array. And then what we're going to do is for each clause in clauses, we are going to, for each our result in clause previous, we're going to yield that. So see, what we're doing is we're taking these environments and feeding them into each clause. We kind of rewind, and this is kind of the beauty of this sort of thing. Disjunction is a little hard to implement in some logic languages because you have to put the environment back the way it was for each clause. Like if clause 1 mucks with some variable, we don't want to pass that into clause 2. And so if they're stored in some global state, you got to be careful about that. And in addition, though, we have these immutable environments, right? So we can throw them through one at a time. We just don't want to reevaluate the this enumerable every single time. So we're going to do it this way. We could do it the other way, I suppose, but it would be very inefficient very quickly. So, okay, we have these OR clauses, and this is complaining that we've done something wrong here. Here in this disjunction. First of all, let's actually make sure this disjunction works. Goal tests. Fact. So what we're going to do here is var results var1 equals that, and then var result in this query. What we're going to do is we're going to say .or range of 0 to 3, and we are going to put that into lvar1 or oh no, and then we're going to do a second clause. It says env range of 5 to 8. So unlike our conjunctions, we're going to say it's 0 to 3 or 5 to 8, and then we're going to get that. And the result should be 6. And result should be equivalent to. So this is correct. We have 0, 1, 2, 5, 6, 7. And where's our can use disjunction? No, we need to delete this for now. Yep. So see, we kind of run it through two separate places. These don't collide and they don't unify out, because in this case, in this branch, it's 0 to 3, and in this branch is 5 to 8. It comes out and goes into the run. This is one of the reasons why I wanted to do this too, because this syntax is a little weird, where we're using them in the inner branches as well as in the outer. All right, so let's get back to our member row just for fun. Okay. So this is saying we get the rest of head and tail. And then we say it is either, member row is either, no, that's not right. Or is it? Yeah, it's either the head is equal to the item, or we recurse again with the tail equal to the item. Yeah. We're going to rename this just so we don't get confused. Okay, so what we're doing is, so first of all, breaking this apart. We're breaking the list out into head and tail. And then we're going to say, we're going to bind it to the head, right? Or recurse again with the tail and the item. So we go up here and we do the tail. And that's going to keep on going until we hit the end of the list, because this will fail to bind and the whole thing will terminate. Now, if I'm not mistaken, this will cause this whole thing to fall apart, because it should go into an infinite loop trying to construct that IEnumerable structure, which is kind of one of the benefits of not using enumerables here and using, what do you call them? Using monads. But let's look at the, if we can do that here. So, values via member. So, var list equals lcons.create 0, 0, 1, 2, 3, 4, 5. And then var lvar1, and then var query member row, and we want to get, well, we could get item 3, but we want to bind it to every single one, lv1. And so what this is going to say is get us every single one of those. The length should be 6, and it should be 0, 1, 2, 3, 4, 5, because it's going to grab every one of those items. And so let's see if this works or if this blows up. We may get a Stack Overflow here. Yeah, we're getting a Stack Overflow, that's why it's taking so long. So what I have done in the past for this is implemented a new type of goal, which is called recur. And recur. And then we just have this, a single function of IEnumerable to IEnumerable. And that's our argument. And what we are actually going to do is we are going to recreate this entire subsection of the AST on each environment. So, no, that's not what we want. For each environment in E and environments in E and V, what we're going to do then is for each result in calling args with E. And this is a little bit sucky, but we got to do this too and put it in a little box there that return the result. Now it's interesting enough, this is actually just select many. Fun fact, select many kind of comes from the monadic form of that. So, I mean, there's a lot of cross-pollination here. The guy who wrote select many was a big fan of OCaml and Haskell and that sort of thing, where monads are much more prevalent. So now we can go do is down here, we can do E, and this is just going to do recur of E again. We'll name this something else. So let's name this T. And then we're going to pass in, is that what we want? Actually, no, we want this, don't we? What we want, because recur doesn't actually take, oh no, T This is t and t dot recur. There we go. So this is a little bit of a sucky syntax to have to use here, but let's see if this works. Expected it to be 6, length to be 6, but found 3. Interesting. What did we actually get then? Which ones did we get? No, it's not gonna, we need to go here. I suspect we are missing something with this. It'd be interesting to see if it's the same value every time or a different set of values. So the result is 1, 3, and 5. We're somehow skipping 1, 3, and 5. We're skipping 2 in our member row here. Did we botch it up when we did the select menu here? I'm going to redo this so that for each, so I just can step through this and know what's actually going on. So the first invocation of recur should be in our environment. So this is our environment at this point. It's kind of cool to see that we have the head, we have tail. So the head is 1. Oh, LVAR 2 is head, and LVAR 4 head. It's like we've pulled the head off twice, which is a weird thing to say. Are those 2 different heads? Let's see here. So we have head 2 and head 4. Okay. And then the first environment we get out of this has what? Oh wow. We have the head 7 is 2. Okay. Doesn't look terrible. Could probably use to have results of this a little better. Let's find this environment. It'd be nice to make this an IEnumerable of like LVAR to object. Okay, I don't know why they added that in. No, that's not what I wondered at all. What did that do? Don't put missing members. It's not what I wanted. One equals. What I want is the Okay, thanks, JetBrains. And then we're just going to do for each our key v and bindings. And then yield, return, kv key and kv value. Yeah, this isn't an override. And then public IEnumerable, get enumerator. No, it's not enumerable. Wow, I am slipping. I may have to think about this and come back to it. And this is just going to be an IEnumerable. Because this needs to be the non-static version of that. My brain's too tired at this point for this. So we're just going to rip this out. But I would like to figure out what's going on with the membero. Let's see. Let me go up to another page here and see if I can figure out how it's done in Core Logic, which I've worked with before. Which is a closure variation of this. I think there's an equals in one of these places too, and I think I'm missing that. And it's been way too long since I have done this. I'm looking it up in the Core Logic code base right now to see. Okay, so this is their definition. So in Core Logic's version, it's this, and this is a little hard to read, but it's saying pretty much the same thing, although they are doing this lcons thing inside of here. So let's do that, because what they're saying is it's either they have this define pattern thing. So they're saying it's where, yeah, so they're putting the rest in each section, so we can do that, no problem. I think that might be the problem here. And then in our recur, we're going down here and we're doing this. And this is more for just example of how this works. I don't really expect anyone to think about this or know how it works at this point. So they're doing head, tail, where X is, well, they're destructuring this into head, tail, where X is a member of the tail. So they do have their parameters switched around as well. So this is X is anything where X is the first item in the tail. And then this is anything where head is the thing of the tail. A relation where L is a collection such that L contains X. Well, I don't know that we have to do it this way. It's interesting that they do. Let's see what our tests give us if we do this. Still found 3. It's like we're jumping twice for some reason. We're skipping ahead. That could be in our well, it's not really in our disjunction. We did test that. Let's look at this again. Resto is the list that's being broken out into head and tail. Such that But we're actually just, yeah, we're not, actually that's not right, because it should be item. We're breaking this out so that the first thing goes into item. And then we forget about the tail. Yeah. So we can implement that in terms of that. What happens when we do that? No. So it's either a resto. No, it's actually either firsto of list is item, right? So either the first thing is the item, or oh, I think that was the problem. We were doing resto here instead of equals. Or the rest is the tail, and the item is in the tail. Those are our two options, right? That works. Yeah, I just got that wrong. Whew, it's been a while since I've coded this stuff up. So if we take these out, we'll see that in fact, when we get down here, we get a result, which is 0 through 5, right? Now, what does this really get us? Well, we can do some stuff like, you know, we can say list 1 var list 2, and we're going to do like 2, 3, 0, 2, and 3, right? And what we're going to say down here is we are going to say, get us all the items that are in both lists. Right? Where LV1 is a member of 1 and a member of 2. Now, this is obviously not going to pass our test, but if we run this, what we should see is 0, 2, and 3 being the result. We have 3 results, and it's 0, 2, and 3, right? So we can build up this set of declarative logic, if you will. And there's all sorts of things we can do with this, and we'll dig into that later. But yeah, it's a good stream for tonight. If you can think of it this way. Why are we doing this? Well, I find it interesting to look at some of these primitives and say, hey, okay, we're using enumerators. Can we use something else? Can we use structs for part of this? Can we store some of these LVARs on the stack or in you know, pools, object pools, and that sort of thing, get better performance out of it? But also when you think of it, I mean, this is the basic of a database. You can write things like, hey, find me people where their name is something and their age is above something else. That's how this is used often, but it can also be used other ways. There's also a interesting thing here, and we'll try this. I don't know if this is going to blow up or not. I actually don't know at all what's going to happen. So we are going to see what happens if we run this backwards. Because one of the things that you can do with muKanren and muKanren is run things backwards, which is really kind of a weird idea. So get me have LV1 be a list of which 4 is a member. Just give me something where 4 is a member, and get 4. Give me 4 lists where 4 is a member. I have no clue what's going to happen here. We got a result. We got 4 items, and look at this. The first one is 4 with something, an LVAR as the tail. The next one is, I don't know how that's right. I think our printing may be off here. Yeah, no, that didn't work. I'm gonna have to debug this. But what you should get out of this is a system where the first item, I mean, if you were to think of it like this, what are the lists that we could get out that have 4 in them? Well, the first one would be 4, right? And then it would be 4 and something. And then 4 and something and something. And then maybe X and 4. And then X and 4 and X, right? There's an infinite list of things that you could get that have 4 in them, right? But if we were to build up more complex query clauses, this might actually be useful, and it is. You can do things like define a set of constraints and then say, instead of just saying, does this pass this constraint? And it says no, you can say, well, give me all the situations that would pass these set of constraints. And you can use that for debugging and that sort of thing. To say like, instead of just asking your database, do you have any people named John? No, what would be the type of database I would have if there was someone named John in it, right? So a little crazy talk, but it's fun. And if you look up muKanren on YouTube, there's just piles and piles, or muKanren. Look up muKanren because that's kind of the parent language, and they mention that here. muKanren is the kind of the big daddy of this. And then they kind of kept reducing the language more and more down to this muKanren, which is this really tiny kernel here. Yeah, cool stuff there. And if you go on YouTube, there's a whole bunch of people talking about it and doing all sorts of crazy things. But thanks everyone for watching. It's been a good little evening of streaming, blowing off some steam programming, and I appreciate it. Hope to see you stop by soon. Or stop by again, that is.